All right, everybody. In class, we talked about relating the viscosity of a fluid to the force exerted on it by a moving surface and how you can use that to find the viscosity of a fluid you don't know. I promised an example. This is it. What we have here are two concentric cylinders with fluid filling the gap between them. This is actually a real type of viscometer that you might find in a lab. The outer cylinder is stationary, the inner cylinder is rotated. We can measure the torque on that cylinder, and then we can use the relationships we've already learned about to discover the viscosity. This is a rotational system. This might confuse and frighten you because it may have been a couple of years since your freshman physics class when you learned about torque. But in principle, this is no different than any other problem that's relating viscosity and force, which we will see. So I will talk you through the rotational parts and everything will be wonderful and lightness and good. So how do we start? So we're relating force and viscosity, right? Viscosity is what we're trying to find, and we've been given torque, which is related to force. So what do we know about that relationship? We know that shear stress is equal to the force applied by that moving surface over the contact area between the fluid and the surface. And we also know that it's equal to the viscosity times the shear rate. And this is we're assuming a Newtonian fluid here. So first off, what we want to do, we need to know what the shear rate is. And so we're going to make an assumption. We're going to assume that the fact that this is curved, the curvature doesn't have a big effect on the velocity profile and the flow. And this is an assumption we can make because this radius right here of this big cylinder is large compared to this gap that we're looking at. And so we can assume the flow there acts essentially like the flow between two parallel flat surfaces, which is what we discussed in class. And what does that mean? That means we can say that the shear rate is equal to U over L. In class, it was U over H because we looked at two flat surfaces and we called this distance H. But in this example, we're calling that distance L. And what is U? U is going to be the velocity of this moving surface, the tangential velocity. Do we know this? No, but we know the rotation rate and we can convert into Cartesian coordinates. So that's what we're going to do now. We're going to set up our relationships between the Cartesian and rotational coordinates. So U is going to be 2 pi r times n dot. This makes sense. And with every rotation, we move 2 pi r centimeters. And then, then you multiply that by the rotational rate. This is what you get. And now we need the relationship between force and torque. Torque is R cross force. And in our case, we can just go ahead and say RF. That's how the cross product works out, okay? So we have that. What else do we need? We need what this area is. So this is the contact area between the fluid and the moving surface. We're going to assume that that inner circle, that inner cylinder, is entirely coated with the fluid, in which case the contact area will be the circumference of the circle times the height of the cylinder, which we'll call H. That's the area of a cylinder. Alrighty then. So what do we want? We want the viscosity. And now with all of these relationships I've set up, we should be able to get to the viscosity from what we know. So viscosity is equal to force times L over A times U, which is going to be torque over R times L over 2 pi R times H times 2 pi R times n dot. And so we simplify this and we will get T times L over 4 pi squared R cubed H n dot. We know all of these values are given in the problem. I'm not going to substitute in the numbers right now, but I want you to, at home, just to check your calculations and your unit conversions and everything. And the correct answer that you should get is equal to 0.158 Newton seconds per meter squared. If you don't get that, double check your calculations. You're probably not converting from minutes to seconds correctly. This is at SI units. Act accordingly.